So there was a very kind of smooth transition from that stream to this. And Carlos basically suggested let's move on and do this stream because we're basically going to have basically the same conversation. So I think maybe there's three things to discuss during this stream because we haven't had a stream in a while because of the winter school and holiday season, et cetera, et cetera. We haven't had a stream on this topic in a little while. So first, I might just summarize for the internet record, et cetera, some of the points that I've been making about this. We've been trying to establish a theoretical framework in which we can couch our observations and the conclusions we've made from our observations by doing all these mathematical experiments. I might say a little bit about the thoughts I've had. Carlos has also had his own thoughts too. And one good outcome from this stream would be to put those together. And I mean, Carlos and I, we can always email about this and we can discuss this further, but let's try and see what we can do in terms of pairing these two things together. Okay, so what have we been doing? Well, for those of you who have seen this stream series before, you know, the key initial source of intrigue was our observation following the work that Nick and I had done with Stephen on mathematics last year, and my gosh, even the year before, technically. Nick, it's 2023. We started that research technically in 2021. Wow, time flies. Anyway, the initial observation that you could take something which in foundations of mathematics you usually regard as being highly fundamental, and that is something like an axiom system, and you can technically emulate it using even lower level computations. So you take something like Boolean algebra, for instance, and you can compute the same results as one would compute in Boolean algebra, but with an emulation using something like an SK combinator, where instead of having true, false, V, wedge, equals, negate, or even true, false, equals, NAND, you just have S's and K's. The arguments and the operators are the same. You can express equality or equivalence using the combinators, so it's more parsimonious. However, so we can do this, and even in the multi-way case, where you have many different evaluations that lead to some fixed point, it confluently tends towards the same fixed point, which is just a feature of SK combinators, as it so happens. So we can enter, some emulation where it's like, and of false, false, and instead of just writing it in the Boolean style, you write it in the combinator style, but in the end, you get the right answer. You do get the right answer, but we do notice some differences. So one difference is that it takes a long time, or it takes longer. You have to evaluate for many more steps. And also we find that the emulation is not really respected in the middle, where we have some initial state and we have some final state that are nice emulations that we can understand. And the states in the middle are very kind of difficult to follow. And that's because we're basically just following combinator rules at that point, even though the emulations at the beginning and the end happen to be more or less the same. Though there will always be one path where you basically are just literally following these exact operations, but then even something like performing and or, instead of taking one evaluation step, it'll take something like at least four, I think, like for and. We'll take like at least 4 steps. So it obviously takes longer. And so we're trying to come up with some sort of a framework for theoretically describing what's happening. And it so happened that when I first met Jonathan Gorard a few years ago, we were on some stream and he had discussed his interest in considering category theory as informed by computational complexity theory. And I had sent him a message saying that I was also interested in that. And I had this interest, but I had not really pursued it. And Jonathan had even kind of encouraged me to pursue it, or later made fun of me for having not pursued it, et cetera, et cetera, et cetera. But I could never find a good test case for actually pursuing that approach. Finally, I think that this is a very nice case in which we can do it. And what I have in mind is, it seems as though you have some particular rewrite rule, or you have a set of rewrite rules, and when you run them, given some initial condition, you have some actual rewrite system. And you can consider pairs of these, pairs of rewrite rules and rewrite system. And you can imagine other rewrite rules and other rewrite systems. And perhaps you have ones where they correspond, as we see with this case of Boolean algebra and SK combinators. However, you're going to have complexity trade-offs. So when you map from one rule set to another rule set, perhaps one rule set is more parsimonious, perhaps it's less parsimonious. Well, in that case, you either have a decrease in algorithmic complexity or you have an increase in algorithmic complexity. That is, the objects, the number of symbols involved, the description length required as you're writing this rule is either getting more or less complicated. So when you're going from true, false, NAND equals at least to SK, you're simplifying your rules to some degree. However, you're also seeing an increase in time complexity with respect to the rewrite system. So you make the rule set simpler, but the actual evaluations take longer. And so what I have in mind is we construct some sort of formal mathematical object using category theory where we're taking pairs of rewrite rules and rewrite systems and we're passing between them. But these morphisms, if you will have attached to them complexity data. When I go from this rule to this rule, is the algorithmic complexity increasing or decreasing? When I go from this rewrite system to this rewrite system, where under emulation the initial conditions and fixed points are the same, is it taking longer? Is it taking more time or less time? Are we gaining or losing time complexity? And my kind of conjecture, which I really like to kind of test, I'm not sure what would be involved in proving it. It would be beautiful to prove it. It would be at least satisfactory to demonstrate it with great conviction using experimental mathematics to show that there's some trade-off of some kind between algorithmic complexity and time complexity. I'm not sure if it'll be one-to-one, maybe it'll be some sort of nonlinear trade-off. Maybe we can run a number of experiments and try and come up with some, there's some constant, or it's something is proportional to something squared, or maybe there's some nonlinear relationship. I'm not exactly sure what it'll be. But it would be really wonderful to kind of establish, in general, you have some sort of rewrite rule, rewrite system, or more abstractly, you have a constructor and some sort of construction, and passing between these construction pairs to other ones, there's going to be some trade-off between the algorithmic complexity and the time complexity. So this is what I have in mind. I think that it'll even help us understand things like the physics project. The physics project is basically right now in favor of high, low algorithmic complexity constructors. However, it seems as though if this is essentially equivalent, then it tells you something deep about there being no free lunch when it comes to complexity. You can pick a very elementary constructor, but then your constructions are quite elaborate. And in fact, from a theory point of view, then you have to assemble a quite sophisticated interpretive framework for understanding your construction because it's so inefficiently built that you're going to have to find some way of making sense of this elaborate behavior that you're seeing. Or you'll opt to take a constructor that has greater ontological richness built in at the start, which gives it greater computational capabilities from the start, and then the rewrite system is much more efficient and takes less time, and then you need to construct a less elaborate interpretive framework because your framework is mostly paired with the ontological commitments that you've made in the rule itself. Okay, so that's the general idea. Now, this needs to all be made much more concrete, and we need to really pair this more closely with a nice general theoretical treatment of rewriting. And it so happens that this part, which I have not thought about, Carlos has thought about. He's thought about it, and the interesting thing is that it doesn't pertain to hypergraphs. Hypergraphs are the main character of this whole story. So with that setup, Carlos, please go ahead. Tell us about the thoughts that you've been developing about hypergraphs and rewriting.
Yeah, it's actually a wonderful follow-up because what you just said, I think this presentation in terms of hypergraphs can make ideas much more concrete, and we can hopefully end the stream with some concrete sort of points of action that we can follow up. So let me see if I can share the Blackboard that I have on the tablet. Things should be possible.
Okay. Okay, I'm excited about this.
Yeah, I can see that. So imagine you can see that.
I can see it. I can see it. Are you gonna?
Okay. Uh,
You can actually write on this in real time.
I can. I mean, I have
Okay, that's
mostly
cool.
pre-written it, but I could. Um, right.
Yeah, that's nice.
So basically, to make formal system concrete, that many examples, ASCII combinators, Boolean algebra, all the things that we've mentioned. There's this pattern that we've noticed. Nick and I discussed this a few weeks ago, and I just had noticed this pattern a couple of years ago, and I've been thinking about this for some time. That by using labeled hypergraphs, you can basically capture all the diversity of formal systems that we've considered. So what I mean by a formal system here, and what I'm proposing to take as our working model of formal system, is that of a rewrite system, of a hypergraph rewrite system, where hypergraphs are actually labeled hypergraphs. I'll explain that in a second. And rules are, the kind of thing that the Wolfram Physics project has been using, the double push out sort of framework that people are using in categorical treatments of rewrite theory and things like that. So I'm gonna explain it very, very succinctly for the benefit of viewers.
Okay.
What is a label hypergraph? Just very briefly. So for a label hypergraph, you have a set of labels, and when I say set, I really emphasize that it's a set and not a multiset, not a tuple, but it's a set.
Okay.
Distinct elements. And then a hyperedge is a data structure built from that set. And by data structure, you can take your favorite formalization of data structures. I particularly like combinatorial species because it's naturally categorical, but really anything goes. I mean, you can also do things very pedestrian with just multisets, and you can do bags of bags of bags, and you can make tuples and cycles and all kinds of things. So, but just more intuitively, you can imagine that you take some elements from sigma, from your label set, and you basically build your little packages of information. So a tuple is a sequence that has a first and a last. A bag is something that has no order whatsoever. A cycle is something that has cyclic order, etc. So a hypergraph is going to be a collection of such hyperedges. So technically, it's going to be a multiset of such hyperedges. So just to show an example, hypergraph H, you can see, it has a tuple AB, has a cycle ACD, has two bags AD. So you can plot this, and it should look like that, right? It should look, ignore the arrow below. It should look something like that, where AB here. I don't know if you can see the pointer. Maybe I can just draw. So this AB here corresponds to this arrow here, right? And this cycle ACD corresponds to this cycle over here, right? So
Okay.
So yeah, so that's just a labeled hypergraph. It has the structure of a hypergraph, of a traditional set theoretic conventional mathematical hypergraph, as a skeleton. So you can always project this down to an unlabeled hypergraph, which basically removes the labels, right? And you just keep the hypergraph structure. So the interesting thing about the skeletons, which I think are the data structures that we're going to be dealing with the most in a technical sense, is that they are dual to hypermatrices. So hypermatrices are, I call them hypermatrices. Some people would call them like direct sums of tensors or whatever, some terrible mathematically inaccurate name. So algebra here yet. So hypermatrix is basically just the sort of the adjacency data put into matrix form. So in graph theory, you always have this duality between the graph and the adjacency matrix. In hypergraphs, you have the hypergraph and the adjacency hypermatrix, and now you have this grading by order, and you go, this first hypermatrix here. So this first component just corresponds to the hyperedges of order 1, meaning involving only one vertex. This matrix corresponds to anything that is graph-like, so it's the two vertex edges, and then this cube will be the 3 vertex edges, etc. Right? So in general, you have this direct sum of things, and so an entire hypergraph is captured by this hypermatrix, which algebraically are very nice objects, because these are matrices in the general sense. It's very efficient algebraically.
Okay.
So so just before we move on to the point, putting things together with your idea of complexity, let me just briefly explain this paradigm of rewrite rule. So for people who are familiar with the Wolfram physics model, this is exactly what has been used. So intuitively, you already have the concept, but we have to be very careful because there's a huge degree of freedom how to define rewrite rules of hypergraphs. And in fact, part of my proposal later on will be exploring types of rewrite rules, because I suspect that depending on what kind of type of rewrite rule you consider, you get extremely different behaviors and you get extremely different looking theories. So the general notion of a rewrite rule is summarized by this diagram here, which is what normally people call the push out paradigm. And when you put it into context, it becomes a double push out. So just so this diagram here, basically, this is a diagram of morphisms of hypergraphs. So you have to choose some hypergraph category. So assume that we've chosen some natural, maybe undirected hypergraphs or something for the sake of example. And then you have basically three hypergraphs that you're considering. You're taking a context, which is basically what's going to be preserved under the rewrite, and then you have an input and an output. So the diagram, I think it explains what this means, right? So you imagine that you have a rule that basically says X, Y, Z are vertices, and you have some edge, ternary edge there. And again, that should also probably carry a variable label if you wanted to, because this is completely generic, right? These are sort of placeholder elements.
Sure.
And then that's your input, that is one hypergraph. And then the rewrite in this particular case takes this undirected hyperedge to two directed edges between XZ and YZ, right? So
Okay.
just one example. So that new hypergraph is the output. The context is the thing that is preserved. And to some people, this might feel very redundant, especially if we are to code this into Wolfram language, because the context is obvious, because you're providing it when you code. But mathematically, it's super important, because otherwise, I have labeled X, Y, Z, those things, but I mean, only I know I've labeled those. Mathematically, those are just three elements, and it could be anything, right? So
Got it.
So anyway, so with that vast amount of there's a huge amount of freedom with this particular way of doing rewrites. It's not the only way to do rewrites, but already that gives you a lot of freedom. I mean, just to remind viewers that if you do this kind of rewriting, you can get basically all the formal systems that we know. All the category theory, all of algebra, all of model theory, all conventional axiomatic of set theory. You get everything out of this way of doing rewrite. So you get finitary mathematics. You get the finitary version of any mathematical theory with some choice of states, which are some kinds of labeled hypergraphs, and some choice of rewrite rules. And this is just a claim I'm making. I'm not giving a proof, obviously, but it's intuitively kind of obvious that you get that. I mean, if you think of, just for people who are familiar with category theory, you can see that if I wrote something like this, X, Y, Z as my input, and I wrote this particular hypergraph as my input hypergraph, and I take this into this way, into something that looks, X, Y, Z. So X, Y, Z is the constant is the context that gets preserved, and you get something like that. That's exactly morphism composition in a category, right? Or, if you want units, you can take X as your element, and then you can draw something like this, X to X, and that's the unit on its object. So you can capture many mathematical theories this way. So how does this connect to what James was mentioning? So it's a question about the complexity of hypergraphs. So obviously, I mean, there's two levels of complexity that we can discuss, but I think since we are now first considering hypergraphs as our ground to sort of fish out some of the models that we want, the first approach is to talk about the complexity of hypergraphs themselves, and then we can think about complexity of the rewrite systems that emerge by choosing rules. But first of all, just thinking of hypergraphs, you have some direct measures that you can take out of a hypergraph. So this is the cardinality of the vertex set. This is cardinalities of the graded cardinalities of the hyperedges. You can maybe go by edge order, and then you can say, the same cardinality applies to each order, and you have a grading. It's quite natural. So this is the analog of something like string length or something like that, right? When you have a string, which is a very special kind of hypergraph, which is basically just a sequence of pairwise edges. The length of that path is essentially the cardinality of the vertex set, or the cardinality of the edge set, more accurately. So more generally, you get that. Now, when rules are present, I mean, that's kind of everything you can do to a hypergraph, unless you want to really assume something quite strong and be far less parsimonious. Now, when rules are present, then you effectively get a way to travel between hypergraphs, right? Because then you can apply something to a hypergraph and you get a new hypergraph, and you start to get, they're not maps, because it's not like you get maps between hypergraphs, but you get assignments between hypergraphs. So you effectively define relations in your universe of hypergraphs, in a set of all possible hypergraphs of your theory, whatever those might be in its case. And so the idea is that when those are present, you can then assign, for example, path lengths to pairs of states, right? You have two hypergraphs, and if they are connected by rewrites, then you can just assign path lengths, and that's another metric that you can naturally assign there. Now, one point that I wanted to emphasize there, this question mark here, is that it's not obvious to me how this intuitively captures complexity in any general sense, because rules, I mean, in other words, this is going to depend strongly on what the rules are, so that path length path length for the rewrite graph, that's only going to be complexity when the rules can be interpreted in some constructive way, or some kind of computational way that is not just completely general rules. And I say this because the types of rules, and this is where the types of rules become super important, because you can imagine, I just listed 4 types just by words: additive, subtractive, conservative, and chemical. These are just intuitive words that I'm going to explain briefly, because
sure.
So if you have something like, when I say for generative rules, we can always take some distinguished initial states and apply ideas of algorithmic complexity and assembly theory to give something like the construction of a hypergraph, right? That you want to think of a hypergraph as being built from something smaller, in some sense. This is intuitively what I got from what you were saying, James, and what this general idea of, in other contexts of like SK combinators or other formal systems, what a complex program is, and Kolmogorov complexity and so on. They take this approach of the size of something, and you eventually measure the size of something. To me, it only really makes sense to, which is in some sense a path distance under some rewrites. It only really makes sense when you have initial states, and you have a distinguished set of initial states, and you have a clear sense of what it means to generate and to construct in your theory. And I say that it's kind of an obvious comment what I'm making, but it's important to realize that the rules, the generality of rules that we've introduced, allow for things that look nothing like the kind of construction that we have in mind, right? Because you can delete stuff and be completely subtractive. You can be conservative and only like reshuffle things around, or you could be, more interestingly, in my opinion, chemical, which is what category theory is like, right? Like the composition in category theory, composition of morphism is kind of a chemical type interaction where you have two morphisms and they sort of react together to give another morphism. So that sort of rewrite rule doesn't look like the traditional, you have something and then you iterate it and you get something more complex. It's something in between being additive and subtractive, because you subtract some things and you add some other things, and So anyway, I just wanted to bring this up to frame the conversation, and how you might want to make the ideas about runtime complexity, which is what I would assign to more like path lengths within the rewrite system, and algorithmic complexity, which is something that I would assign more like metrics on the hypergraphs themselves, right? So anyway, this is just context that we might now discuss.
That's interesting. because suppose the argument could be made. Okay, so computing the path lengths shouldn't be that hard. I mean, Nick suggested, for instance, you take a causal graph and then you're just counting events along the path from the initial condition to or from the initial operation to the final operation. That's not that hard. The question is, I think the more difficult question is come up with a uniform way of measuring the algorithmic complexity. And I suppose, am I right in saying, Carlos, that the idea is, well, if you're going to compare,
You can also infer the algorithmic complexity from the causal graph too, because as soon as you have a path of a computation from one state to another, your causal graph not necessarily linear, right? You have a bunch of events run to parallel. So basically have a diameter, you have the interval between your minimal and maximal element, which is your initial states, or maybe some outcome, right? You can measure this subgraph in different ways.
well, but Nick,
events.
you're supposed to, the algorithm, what I had imagined is you'd have some actual measure for the actual rules themselves. So like the simple example is if I have, let's say I have some rule and it has like 10 different symbols in it versus I have some rule that's like, X goes to X or something that one of them is far simpler. Now, I guess the question though is if we're is the idea, Carlos, that you would take all these rules and we kind of compile everything down to hypergraphs, and then we would use a hypergraph. The hypergraph is this kind of common medium for understanding all of these, since we can always express them in terms of hypergraphs, and then we'd have a more uniform way of comparing even the rules themselves. Is that the idea?
Absolutely. I mean, that's part of the project for sure. Like, that's main. I didn't mention it today, but it was mentioned before. This is exactly why we want something like labeled hypergraphs, which are very simple mathematical structures, but they seem general enough to capture all the formal systems that we've dealt before. Now, if you say that you want something that measures the complexity of a rule, as Nick was saying, I'm not sure that you can say much more than, because a rule is nothing more than 3 hypergraphs, right? Like one of the advantages of this approach is that a rule becomes as concrete as the states. I mean, it is computationally as concrete as the states, right? You have a state is just one label hypergraph, and the rule is just 3 hypergraphs, right?
It's an event that has 3 hypergraphs. A rule only has input and output. If you just
wait. A rule is not an event, though, right? The event is the actual application of a rule.
Yeah. The rule. The rule. I mean, as I said, I say 3 hypergraphs because I take the context as one of the hypergraphs.
Yeah, the context. Yeah.
Just for bookkeeping. It's not a very deep thing to consider.
Now, one thing that will be interesting, right, is right now if we compare Boolean algebra and SK combinators, in some sense we're comparing apples and bananas, or pick your fruit, but they have to be different kinds of fruit, right? They are different.
Yeah.
It will be interesting if when we compile these things down to hypergraphs, that the rules actually are really not too different from one another. I mean, this is the question: is like, let's say you take the SK combinator rule, you compile it down to hypergraphs. Are those rules going to be more or less complicated? If you take something like Boolean algebra and you compile it down to hypergraph, will that rule be more or less complicated?
Yeah,
I mean, when they're distinct, you can do things that are easy, like compare how many symbols are involved.
This is something actually for the next time that either we meet or we have a stream, I can basically show you the hypergraph version of these things just to see what they look like, and you can have a glance. But my comment is that when you have your rewrite rules, right, because they are just 3 hypergraphs or input-output hypergraphs or whatever, there's very little that we can say, right? And that's why I had this section on hypergraph complexity, because there's very little information in a hypergraph. I mean, let me put it this way: there's very little information beyond cardinality in a hypergraph, right? So you can count stuff. I mean, that's what all the people in hypergraph theory is doing, and it's very boring. Like you can count stuff,
Yeah.
and I'm not saying that we shouldn't. It's not it's a bad thing to count stuff, but I think that to be able to compare rules directly, just rules in isolation without reference to states, you can only basically talk about length of like string length, the hypergraph equivalent of string
Yeah.
length, right?
Well, I mean, the standard definition of something like Kolmogorov complexity is it is the minimum description length,
Yeah.
for instance, right?
Yeah.
So, I mean, this is why I say this thing about apples and oranges, is if we wanted to compare SK combinator rule with Boolean algebra rule, we need some common, numeraire. We need some common currency where we're going to compare these two things. And if the point is that we basically, if our hypergraph rules are our descriptions, a common currency for describing these two descriptions, then yes, it'll be some boring thing like counting, because we're trying to assign some measure to this common medium for encoding these rules.
What if we just calculate the entropy of hypermatrix? And then the rule is like a par or triple of graphs. So,
But hypermetrics is not a property of a rule. It's a property of a hypergraph, which the rule has three.
but then we have
Carlos
the notion
is-
of entropy of hypergraph, and rule is two graphs, so maybe like.
But yeah, Carlos's
maybe
point is that the
something like
rules
difference
themselves.
between hypergraphs. I don't know.
Yeah, I mean,
But Nick, Carlos's point was that you can describe rules in terms of these hypergraphs. I think that was kind of Carlos's point, right?
Yeah. I mean, my point was not that we cannot do it. My point is that what you're going to get out of it is mostly some kind of string length complexity, right? So it's
That's not a terrible. That's not a terrible outcome.
I know. I'm not saying it's bad. It was just a comment. It was not a negative comment. It's just saying, yeah, we're gonna. And I think it's a good place to start for sure. I think Nick was pointing at what I had mentioned in this notes here, which is that once you have the causality in place, right? Once you have states and things changing and evolving in some sense, then I think that's where the actual question of complexity resides. Because you can have some kind of rule complexity comparison, right? But
Yeah.
in my opinion, if I were to say just intuitively now, how to compare the complexity of say Boolean algebra in the usual sense, in the usual mathematical algebraic sense, and SK combinators. If I were to assign these things some degree of complexity, I would like to look at the entire rewrite system that you have. So,
right.
But
But my point is, I'm inviting you to consider both. Because what I want to see is, if it's the case that in the SK combinator case, for instance, the computations you have to perform in this thing we're calling this emulation, which hopefully one day the emulation is just some morphism from a rule rewrite pair to another rule rewrite pair. Yes, the computation takes more time, but the explanation is that it takes more time because the rule is simpler, and so the capacity to do computational work is not as readily endowed in the rule, and so it takes longer for it to actually be computed. So that's why it's important to compare both the complexity of the rule and the rewrite system, because my whole argument is that there's this no free lunch principle where, when the rules are simpler, the computations are more complicated and vice versa.
yeah, I'm not sure that. I mean, imagine that you just want to not all of Boolean algebra, but just one operation, right? Set with one associative operation, just AND, for example. I mean, as a rewrite system, that is one, tree rewrite rule where you have something with brackets or whatever. It's a simple graph to graph rewrite. The S combinator expression has three inputs, and I think it's a graph with 3 elements. It goes into a graph with 4 elements or something like that. So I mean, the complexities are going to be very similar or even higher in the SK combinator side. So it's not with this description already at the SK combinator level. It's not clear
But
to me that
you can take end then in isolation from all other like operators of Boolean axioms, right?
say it again. I didn't hear that, Nick.
You can take an AND operator in isolation from all other Boolean operators.
Sure.
It's kind of weird. Maybe by itself it is actually simpler than just S combinator.
It is. Yeah. That's what I mean. That you can just take that one if you want it, as placeholder for the entire Boolean algebra, and as a rewrite system that's just basically a simple like 2-leg tree rewrite.
The difficulty is, Nick will remember this. We did this exercise where we took the MetaMath library. You could do this with MathLib or something else. And you take something like a simple operator like plus, and you query all of its dependencies. And plus certainly does have a number of dependencies, and will also have a number of dependencies.
What do you mean?
This is
what do you
well,
mean?
what I mean is, for plus, I mean, it's kind of funny. You think of plus as being just some part of basic syntax, but plus has a kind of a meaning. And if you just show plus to someone who's never studied math before, for instance, it's not intuitive. It depends on other relations. And so you could do it with wedge or v as well. And I think the point is, I'm using this concept very loosely. This is what I mean when I say pretension. When I say, if you were to take, let's say you have some rewrite rule, and the rewrite rule involves something like a vector space, or it involves a measure or an algebra or a group or something, right? If you say, let's say I have some rewrite rule and it's, it's a homomorphism between groups, right? Well, it's written very simply as a rule. But when you take, let's say you take a group and you find it in a math database, and then you decompose it into all its dependencies, all the constructs on which it depends. That's going to be a very, for a group, it's going to involve a number of dependencies. And alternatively, if you consider something like an S or a K, I mean, they're highly atomistic. They're not really depending on much. There are rules, but they're depending on far less.
No,
so
but
this is
James, I think.
Yes.
Let me.
Go ahead.
I mean, I think I disagree with that, because you can get. I mean, I understand that in the libraries that exist, that's the case. But I mean, you can define a monoid just with very simple. I mean, in fact, they did it with SK combinators as well. I mean, monoids are just this word concatenation, right? So it's kind of the simplest rewrite rule that you can imagine, and you get monoid side of it, and you throw in some extra cancellation properties and you get groups out of it, right? So I don't know, I feel like you can, I mean, the conventional exposition of mathematics doesn't look like that at all. I agree, the conventional, but you can have algebra basically presented as a rewrite system, and it works very well, and you don't have to make any reference to set theory or anything like that. I mean, some mathematicians will like raise their eyebrows and say, "Oh, that's not real mathematics," whatever. But I mean, as a system, it works as a group, right? Like as a computational system, it is completely equivalent to a group or to a monoid or whatever. So I think it's just a matter of where you place your. That's why you said that you need some kind of reference of, where your ground states are or something like that, because this idea of completely universal simplicity or something like that, I don't think that makes a lot of sense, right? I mean, it should be relational. Complexity should be relational. This is something that always bugs me about complexity, that there's a lot of absolute measures that you are counting stuff and you always have the zero count as a reference, and to me that's a little bit misguided. I'm not saying it's wrong, but it's a little bit confusing or potentially inducing some confusion, because what you can clearly do, we said this in this stream, what you can clearly do is, once you have a rewrite system, you can take, as Nick said, you can just take events and you can start to measure path lengths, and you can relate states to each other. But assigning complexity is to say, these are the simple ones, the non-complex ones are these, and these are this amount far away from the simple ones. And so, I think it has to be relational. I mean, I don't think you can escape. If you're in this very parsimonious way of doing things, you either count stuff and you say we are above zero this amount, and that you always have that reference, or you have to be relational within your system. You can say this hypergraph is complex with respect to this hypergraph in some capacity, which is very analogous to what's happening in observer theory and all this relativity stuff, which is a good confluence, I guess.
Well, one idea that came to mind when you were describing that monoid case is, you see, I can imagine, for instance, I mean, what you're describing, and we see this when people find more simpler ways of describing particular axiom systems, for instance, is again, this is not unlike what we're describing in terms of these emulations. You can imagine the very complicated description of group theory. You're reminding us that when you try and treat these things as rewrites, the descriptions can get simpler and simpler. So
yeah.
Something that I wonder is that perhaps what we'll find is that, yes, you can consider these emulations where there are perhaps really drastic differences in, say, the relative algorithmic complexity between two rules. But ultimately, when you treat these things as rewrites, and a stronger point, perhaps when you treat them as rewrites and they're all compiled on the hypergraphs, perhaps you'll find that when we take, say, Boolean algebra or monoid theory or something, if we take these different emulations and then we compile them all down to hypergraphs, maybe they'll be more or less the same. The complexity measures will be the same in terms of the time complexity, in terms of the algorithmic complexity. That would be quite interesting to see that by making them all rewrites of basically the same kind, then you're converting those. It's like a common emulation. It's a common emulation where you can basically get equivalent algorithmic and time complexities, and that doesn't contradict.
You can do two things with hypergraphs. If you take a single hypergraph, obviously you can describe some kind of complexity of this. You can actually count the number of hyperedges and how many different of them of this particular class there are. You can enumerate all of them.
Yeah.
You can do similar stuff for the rule. You have a signatures for Wolfram models, right? Those signature enumerate actual rules possible with that signature. You can actually take any rule and assign a number, how far it is from this simple signature to its signature, and it's like that would be some notion of complexity. And you can, if you take two hypergraphs or two rules, you can measure some kind of distance between them, and the obvious distance would be how many actual rules of the same hypergraph you're writing you can apply in order to go from one hypergraph to another hypergraph. The like when you can measure it with the same kind of norm that you just described, right?
Exactly.
If you have a simple rule, would be very non-complex. If you just in order to rewrite one hypergraph into other hypergraph with this simple rule, then this rule is not complex.
Wait, but Nick, are you saying that? I mean, would you define the distance with rewrites? I think
yeah, it's like edit distance, Levenstein distance kind of idea, right? How many actual rules you have to apply or edits to one hypergraph in order to arrive at your second output hypergraph. And you also measure the actual which rules, because there are multiple paths you can take, right, from input to output. And maybe the minimal one would be the actual distance, right? Because you can enumerate all the rules and also assign a complexity to all of them. You can obviously then assign the complexity to this distance between any two states, two hypergraphs. And maybe you could do it recursively like that.
So would you? I mean, I guess that
Like,
because you would enumerate all the rules and just count them.
You can count them there. Yeah, but maybe you can just start from the simplest hypergraph. Imagine you have an empty hypergraph or maybe unary hyperedge.
Yeah.
Obviously, that's like how many rules you can apply to get to the different hyperedge of unary arity, right?
Well, technically, as many
Okay,
as there are
one of it.
hypergraphs, right? Technically.
Yeah,
That's the
but
problem,
it
that
requires
we have a lot of freedom choosing rules.
not the rules of the same kind of class, right? Just one unary edge to a different unary edge. So a canonical
Okay,
representation is just the
yeah.
same rule, right?
But yeah,
And
that's
because
yeah.
because it's the most simple rule, and and it requires a single update, you assign a complexity to the unary edge as like the most minimal complexity. You assign it 1. Then you go enumerate, go next, enumerate take a different hyperedge, different hypergraph, and using the rules that you already quantified with the complexity, how many rules you should apply in order to arrive at this new hypergraph from hypergraphs that you already know how you quantify those. Right? And you can build up this structure and quantify all hypergraphs with the complexity measure.
Yeah. No, I get it. Yeah. So basically, taking ISO classes of hypergraphs, and then that induces ISO classes of rules, and then you can define by enumeration. You can define distance between rules.
But then it's highly dependent on the collection of rules that you choose to apply.
Of course. That's going to be. I mean, our first approach is that this is. I mean, the collection of rules that you choose is everything in a way. It's like because that's what we're giving different names to different choices of rules. I mean, the only thing that distinguishes.
Yeah, but if you want a complexity, like sort of independent notion of complexity, like
You have to have an order of your equivalence classes, right? Like if you enumerate Wolfram models, they have a signature, and if you have an order, you can order those signatures. Of course, in each signature you have multiple rules.
No, I mean, first we need to have the ISO classes, and then we can discuss how to assign different signatures or metrics. I mean, because it's not an obvious thing to. I mean, you can either grade by order of vertices of edges. You can just blunt cardinality to the whole thing and things like that. I mean, the signature assignment to hypergraphs is not obvious. But I think first we should have a clear understanding of ISO classes of hypergraphs, ISO classes of rules that we write, which are basically pairs of hypergraphs with a context or whatever. And once we have that, then it should be quite systematic to say, well, if you want this kind of metric emphasized, then these rules are, up in the scale of this particular, which can be done by, as you said, like by taking the simplest one and but we have to fight a little bit against the generality of the hypergraph rewrite rules in this very, very general sense, because they are super general, and they are. I mean, mathematically they are more general than what we do in Mathematica. So we need to.
How about this hypermatrix idea? Is it general enough? How do you distinguish between those cycles, tuples, and bags?
Oh, those are just symmetry properties of the hypermatrix.
Oh, really?
Yeah. It's very nice. I mean, it's just symmetry properties of the hypermatrix. So basically, I mean, it's the usual story with adjacency matrices of graphs, right? Like the adjacency matrix of an undirected hypergraph is symmetric, right? The adjacency matrix of a directed hypergraph is non-symmetric in general.
Well, for example, no, it's like for a graph, you can't distinguish between an undirected edge and two directed edges going back and forth, right?
You can, yeah.
You can distinguish them with the adjacency matrix.
Okay, sure, yes. I mean, you can't, but if you have the symmetry information to generate the equivalence classes under the symmetry, then you can, right? So it's the same idea. I mean, the question is whether you're going to have more or less edges, because each Okay, so the matrix is the adjacent. So the matrix is capturing the adjacency information. So it's the dual object to the graph. So it's not that you're gonna, I mean, you're gonna hit the same edge many times in your matrix, but there's only one edge, right?
Yeah, good. For example, if you have ABC
Yeah,
hyperedge, if it's a cycle,
yeah.
if it's a tuple, you basically have a single one in your hyper.
Correct. Yes.
If you have a cycle, you'll have 3. And if you have a bag, you have like 6.
You have 6.
Because you have
Yes, exactly.
3 factorial. Yeah.
Yeah, exactly. So yeah, it's very efficient because, yeah, the beautiful thing about this matrices, I mean, I call them matrices as opposed to like tensors or something like that because they have all the symmetry information inside, and you can do arithmetic with them. You can, for example, union of additive union of graphs, right? Where you just basically add everything that you had. So if they have the same labels, you put things on top. That's just addition of hypermatrices. It's just arithmetical addition of hypermatrices. So these things are extremely computationally efficient. I mean, they are very nice. So in terms of data structures, you can basically forget about graphs and hypergraphs. You can just deal with hypermatrices as long as you keep track of. And basically,
Okay,
you only work with those when you want to visualize.
Yeah. What if we just calculate the entropy of hypermetrics?
What is the entropy of hypermatrices? I don't understand.
You have a definition of entropy for matrix.
Really?
I've seen it somewhere. I don't know.
But what is that measuring? Like,
Let me find it.
I mean, I'll make a note because this is my homework.
Well, you can imagine, like, I don't know, a matrix that has the same value in every single position is going to have an entropy that is
Yeah.
much higher than one where it's, zeros everywhere and then there's just a one in one particular position. You can kind of,
Oh,
I've seen exercises like that before.
I see. Okay. Yeah.
Yeah. And then we can think of rule as like meta hypermatrix, right? So you just apply hypermetrics to another hypermatrix to get another hypermatrix, and complexity of rule maybe, and entropy of this meta matrix.
Yeah, well, I will have to think about the interpretation of the entropy of a hypermatrix before I will go into that.
Yeah.
But I think it's interesting. Yeah, I mean,
But yeah, but the thing is, you can think of rule as hypermetrics too.
you can,
right?
But
Yeah.
it's not obvious how to do that because there's the input, output, and context, and it's not obvious how.
No, I think this is pretty obvious. You just at every level you.
No. I mean, I understand how you're seeing it's obvious. I'm saying that that's not the only choice.
Yes. But the rule is really rewriting between hypermatrices, right?
Not necessarily, because you could I mean, I-OK are potentially very different looking hypergraphs. So I mean, as I said, it's very general. So it's not like you have a hypermatrix and you rewrite the hypermatrix. I mean, these are 3 hypermatrices that are and the something very important to keep in mind is the hypermatrices do not keep track of labels, and we desperately need to keep track of labels. So hypermatrices are efficient packages of skeletal information of hypergraphs, but
they sort of do if you don't permute your entries. Like if you have a matrix and not
No.
like an equivalence class of matrices with permutations or.
So the point is, you could have, I mean, this diagram in particular, I didn't duplicate A, but I could just have, You know,
Yeah, and A is like the first entry in your matrix, so
no.
or,
But
or,
the problem
or
is
your vector, or
the problem is that the hyper matrix of the hypergraph that was there before with a B is the same as the one with the one with an A. You don't have a way to distinguish that. And the problem is that if you're interested in A as a distinguished element in your formal system, that edge there is actually the A arrow A is actually a self edge, right? So the information it carries is different. All I'm saying is that
once
hypermatrices
again,
do not keep track of labels. It's not a problem. It's just
can you repeat?
if
Like,
yeah, I mean,
how matrices are not keeping track of labels?
so I mean, the explanation is basically the reason why I have these dots here. So basically, what you capture is the structure of the hypergraph, is the connectivity of the hypergraph. But you don't keep track of, and you choose some random order, whatever, you pick an order to make it into a table if you like to visualize it that way.
But if you pick this order,
No. But the problem is that they can be duplicates. It's not about the order. It's about duplicates. So if I, instead of B, have an A, then that edge there, although it looks like a edge between two distinct vertices,
it's a loop.
It's actually a loop. It's a self vertex. Right? So
Yes.
that cannot. It's not a problem. This is not a problem at all.
but
It's just
how, what hypergraph it corresponds to in your setting?
so
Like
the
this skeleton, or is there like one?
the hypermatrices capture skeletal hypergraphs, which are unlabeled hypergraphs.
Okay, and what is the skeleton for the graph that you written with two A's?
The same one. Exactly the same one, a skeleton. And the problem is you have two different labeled hypergraphs
And
that project down to the same unlabeled hypergraph.
Okay, how do you implement this A to A edge in your data structure?
Yeah, that's the question I have too,
One
because
A and
It's a tuple. A. It's a tuple. That's what it is.
A, and if you had a self loop, then what it is?
Well, I mean, it's the same as
my,
whether.
my, my question is, Carlos, you can imagine a version where you make all the labels A's, and then you just have some series of complicated loops. In your the skeleton that you drew, you still have these distinct dots, but technically you could have a number of self loops plus a self loop hyper edge, which I find somewhat difficult to understand.
This is just the usual. I mean, I didn't mention, but I mean, it's conventional to take this simple hypergraph because we want this to be some kind of.
Can you see what I drew?
Yeah, I can see that, but so because you can. I mean, the problem here is, I mean, we shouldn't really waste too much time on this, because the problem here is whether to make the hypergraphs simple or non-simple, and it's just a matter of what you want them for. If you want something like duplicates to be part of the information that you're conveying, which is absolutely what we want, like you want that the string A is not the same as just A, right? So
yes,
because you want that explicitly in your data structure, my suggestion is that we use simple hypergraphs, because otherwise the string A will be just A with like some thing on top that you can track. You can keep track at the level of the data structure. So at the level of the hypermatrix, the things are completely equivalent. That's why I'm saying that you cannot keep track of labels. So the actual hypergraph structure does not change. Right?
So basically you have unlabeled hypergraph, the number of vertices corresponds to the actual dimensions of your hypermatrices.
Yes.
Right?
Yes.
But you also have an additional list of actual labels.
Yes.
If you want. And every rewriting rule takes care of both.
Take case, exactly. Rewrite rules, worry about labels. That's the point.
Yeah.
You need the labels basically to be able to consistently write rewrite rules to begin with. Because otherwise, you're going to get into ambiguities that can be resolved in other ways, but this is the particular way that I'm suggesting.
Can you have a rewrite rule that, for example, will rewrite only this hypergraph that you have drawn here, like with two A's, and not rewrite the graph, which has B instead of one of the A's?
Yeah, absolutely.
Like the rule can see, so the rule sees beyond the hypergraph structure.
Correct.
So
Rule can pose constraints on labels, so it can say that two vertices have the same label.
okay,
The rules apply.
then they're not like hypergraph rewriting rules.
They are. I mean, I'm not saying labeled hypergraph rewriting rules, but they are labeled hypergraph rewriting rules. I just don't want to say that long term.
Yes. So your vertices have internal structure here.
They do. Yes.
And the skeleton sort of comes like at the end of all of things, but at any particular step you cannot just take skeleton structure.
Yeah, the skeleton is always there. I mean, you can always project down to the skeleton.
Yeah.
And the idea is these hypergraphs. I mean, if you imagine what you write down, right? A word, a set of symbols with brackets, a diagram in category theory, whatever. These hypergraphs are meant to model exactly that. They're kind of generalized diagrams, right? So you want this ability to say that two things are distinct because they are structurally separate, but you want the ability to label your data, right? So that's why you put hypergraphs as a skeleton and then you sprinkle a set of labels on top. It's just a convenience. I mean, you could do everything with hypergraphs and be very, worry about the technicalities of loops and self edges and all that kind of stuff. But it's much simpler to go the route of standard using mathematics, where your labels actually carry information, and it's not just the placement within your data structure that carries information. So it's a choice. I mean, I'm not saying that this is a closed thing that,
Yeah, but
it's a
but
choice.
If we actually had like pure hypergraph rewriting rules with structureless vertices.
Well, for a computer, you would always have to choose some labels, by the way.
Yeah, but then we could use this matrix entropy, right? It will be well defined.
No, I mean, we can put
as a rule for pure, let's call it pure hypergraph rewriting rule would have like entropy defined in the same way as entropy of this hypermatrix.
I mean, yes, you can. I mean, I'm not sure how you would assign a single entropy to a rewrite rule, because you have two hypergraphs, or three if you take the context.
Yeah, but think of a matrix, like think like of a regular graph with matrix. So you rewrite one matrix into the other. You can realize that by means of the third matrix, and third matrix basically represents your rule, acting on the first matrix and transforming it into the second. And just do the same on the level of hypermatrices.
No, I don't see the case of the graph. I mean, I don't see how in the graph, if you have a graph rewrite rule, you have two matrices.
You have one adjacent metric of
Yes.
the input and adjacent metric of the output.
Yes.
And you just take a linear transform between them.
No, that doesn't work. That doesn't work in general. Because there's no linear structure here. I mean, we're calling them matrices, but there's no linear structure.
But you can.
They might not be even same dimension. I mean, there's no linear structure.
Okay, they may not be the same dimension, and then what? Like, you.
But how do you take one? I mean, the point is you have two or three matrices. How do you make one to take the entropy out of? I'm not saying you cannot assign an entropy based on matrix entropy to a rule, but just by saying that you get somehow a single matrix out, I don't see how you get a single matrix out. That doesn't seem right. Because I think you're thinking that the matrices somehow operate into each other, but they don't.
Like, when they rules, they do. Sort of.
What?
Like, rules is something that operates on one of your matrix and produces you the other.
No, but the thing it's not, a rule doesn't give you a map between graphs. It gives you an assignment between two whole graphs, but it's not a map. It's not a morphism of graphs. If it were a morphism of graphs, I could make a matrix out of it, but it's not a morphism of graphs. It's an assignment between the two graphs as a whole. It doesn't give you because otherwise you need a map between vertices and a map between edges and things like that. You don't get that information. Rules are smaller. They're simpler than that. they are subaxiomatic in this sense. They are they're beneath the usual mathematical structure. That's why we're using them.
So Carlos, just to review, how do you have a proposal for measuring the complexity of the actual rules themselves?
Yeah. So I would initially do exactly what you said. So you can basically look at the cardinalities of the hypergraphs involved, and the same way that you would say that a rule that involves words that are longer is more complex than a rule that involves words that are shorter, you can make similar statements to hypergraphs. And so I would, for the next time we meet, I can just bring that definition and I can bring that applied to, say, Boolean algebra and nested combinators, and we can see it in the flesh.
Well, that's what I was going to suggest. But first I'll ask Nick. So Nick, I know that Utkarsh has done some work on compiling lambda calculus, etc., down to hypergraphs. We might use some of Uti's work here, since it's always a shame when we forget about work that summer school students did and then we do it over again, or we don't actually take advantage of it. So have combinators, do we have a way of passing from combinators to hypergraphs already, or does that need to be done? Do we have a way of passing from Boolean algebra to hypergraphs already, or does that need to be done? I don't remember.
Oh, as the rewriting rules, they're kind of obvious how you do it.
They're kind of obvious. Yeah.
You just
Okay. Well, but no one has done them. They're obvious, but
I've done it.
Have yet to be done.
I've done it.
Yeah.
I've done it a long time ago. It's like I have general rewriting rule in the language because it's a tree like expression rewriting, right?
Yeah.
So you can compile trees into hypergraphs, and you can form a simple rewriting rules on expression as hypergraph rewritings.
Okay. Okay, cool. Well then, yes, Carlos, I think, finding a way to make functional this definition where you give a hypergraph rewrite rule, and then you propose some way to measure complexity of the rule itself, and then you can feed this, make it into some function, you feed the rule into the function, it gives you some sort of complexity measure. Then we try this for SK combinator rules and Boolean algebra rewrites compiled down to combinators. And then let's see, once you get down to, it's compiled down to hypergraph. Once you get it down to the hypergraph level, let's see how different these things look. I won't be surprised if once they're at the hypergraph level that they're not too dissimilar, but we'll see.
Yeah.
Yeah.
We'll see.
Okay. Well, I know it's late for Carlos, and he's probably hungry, and this is like the time where he eats his first meal. I'm also hungry. And I think it's late for basically everyone besides me. For me, it's very early. So, all right, guys. Well, this has been very fruitful. Carlos, if you like this Blackboard approach to meetings, I was glad to see you take notes, and if you share that. Sorry?
It's sometimes useful just to see things.
Yes. If you prefer to write things than to type things, I have no, particular, quirks about people having to use one thing or another. If you want to do handwritten notes during these meetings, it's totally fine with me. So if it helps you think better or whatever, that's fine with me. All right. Well, for the viewers, people who are watching, thank you very much. If you have questions about any of this, clarification, if you want us to clarify things, if you have an argument you want to make, if you have an idea, if this reminds you of something, a simple question like, what's a hypergraph? A complicated question like, what's a, I don't know, some other thing that we were discussing that's more complicated. What's algorithmic complexity? Whenever we're discussing these things and you want to know more about some of the concepts that are involved, it's never a bad exercise for us to make sure that we have a nice, solid definition of these terms that we're throwing around so casually. So, always feel free in the chat or in Discord or privately, or send me a pigeon with a little letter in its mouth or whatever it is. Let us know, and I'll be happy to respond. Anyway, Carlos, thank you.
Yep.
Thanks for preparing those notes in advance. I learned quite a few things from this, so I found that to be very helpful. So, All right, guys.
Very helpful.
Cheers.
See you soon.
See you next time.
Goodbye.
Bye-bye.
Bye.
All right.